Firstly, let me say what a pleasure it is to be here in Paderborn. I'm so enjoying visiting here. And secondly, I must apologise that I'm having to present in English. I feel very bad about that, but thank you very much for your perseverance with this. Let me walk you through something of the journey that we've been on here. For the rationales to putting computing onto our curriculum in England, the journey that we took from ICT that we had as a curriculum subject to the new subject of computing, what we've put into that curriculum, a very quick tour of the highlights there, and then something of our organisation, Computing at School. So what are the rationales? Why should we teach computer science to young children? Shouldn't this be something which we leave until later, until they get to university? Well, I and my colleagues in England don't think so. We start with children's inherent curiosity about the world in which they find themselves. And these days, of course, computers, digital technology are an almost ubiquitous part of that world. My daughter here, at the age of 18 months, already has a mental model, a schema of how computers work. You close the lid and mummy and daddy pay more attention to you at a very simple level. But you stroke the trackpad or slide your fingers across the screen and the computer responds in some sort of way. Already by this age, Sophie had an idea of input, process, could be magic, output. And we build on that with her curiosity about that world. We have also, though, the notion of computer science provides an insight into the world itself. It's not merely about technology, but there's something fundamental to the nature of reality which says some problems are easy, some problems are in fact impossible, some problems are hard unless you think about them the right way. And those insights into computability, I think, are fundamental to the nature of reality. So teaching a child about the world in which they find themselves, yes, involves an understanding of how technology works, but also an understanding of the principles, I would argue, of computation. I think for our education ministers, the most powerful argument was one about economic viability, that if we wanted an economically sustainable games industry, software industry, fintech industry, digital effects industry, then we needed a stream of students going into university to study computer science, and the best way to ensure that was to provide some early experience of it at elementary and secondary school. I'm not sure this argument wins much support from teachers who feel reluctant seeing the school system as a place for vocational training for the software industry, certainly when you're thinking in terms of elementary education. For many teachers, though, the argument about preparing our young people for a future which we cannot imagine is a persuasive one. For my daughter, who started school a year and a bit ago, I have no idea what the future will be like when she leaves school, when she graduates from university. But I'm fairly certain that digital technology computers are going to play an even more important part in that future than they do in our world today. If there's anybody in the room who thinks that digital technology has peaked and we'll be using less of it in the future, raise your hand now. Okay, right, well here, what would one would expect? I think, though, the persuasive argument is something which goes back to Friedrich Froebel, the kindergarten, and the Froebel gifts. Why do kindergarten teachers, practitioners, give blocks like this to young children to play with? Well, it's basically about an expression of their creativity. It's a medium in which they can solve problems and express themselves creatively. But it's also about an understanding of the world, that the number of blocks doesn't change, the shape of each block doesn't change. You pick a block up and let go of it, what will happen? Falls. Okay? That we have there, through that early experience of playing with technologies such as this, yes, medium for creative expression, but also an understanding of the world. And I think the same is true when we fit blocks of code together in Scratch or similar programming languages. Some of the children who go to learn programming in kindergarten, in elementary school, will go on to become the programmers and software engineers and computer scientists of the future. But that's not the reason for teaching this. This is about an understanding of the world and creative expression. Similarly, some of the children who went to Froebel kindergartens went on to become architects and construction workers, but not all of them did. Famously, Frank Lloyd Wright went to a Froebel kindergarten and says there was much influence between one and his later work as an architect. Right. So, how do we go about this task of building computer science into our curriculum? I think we started, many of us around the table, with Pappert's vision for what you would get from teaching children to program computers. Back in 1980, 36 years ago, when he was writing Mindstorms, at that time, educational software or the use of computers in school was very much about presenting children with learning objects, of giving them interactive activities on screen, of, as he put it, programming the child. Pappert's vision was to move beyond that and put the child in charge of the computer, not as an end in itself, not merely so they would learn how to program, but through being able to program, look at other areas of study, other domains, in a different way. He began to see how children who'd acquired this use of the most modern and powerful technology could establish an intimate contact with some of the deepest ideas from science, from maths, from the art of intellectual model building. That's what we were trying to do. We had children leaving elementary education who were very good at consuming a range of content, who were good at using technology, who were good at using a number of tools to communicate, often things which they weren't allowed to at that age, who were able to read and write in a digital domain. Some definitions of digital illiterate, then yes, digital illiterate, who could, by and large, keep themselves safe, who had a set of skills with which to move on to secondary education, but generally seemed to think that what happened in the machine or down the wires was akin to magic. There are fairies doing this. We wanted to move them on from that, from being consumers of culture to creators of culture, from users of technology to makers of technological artifacts, from communicating to collaborating, from yes, being literate, to more than that, being critical about the digital domain, and yes, being safe, to more than that, acting responsibly in an online world, and adding to their skills some level of understanding about this and replacing the thinking that it could be magic with some actual knowledge. We had this idea that this wasn't just about technology, important as that is. This was about learning the fundamental principles of computer science, that this is the way to prepare for an unseen future, that these fundamental principles haven't changed over the last 20 years, over the last 40 years, even though our technology has rapidly advanced in that time. And that these fundamental ideas can be taught away from the computer if necessary, important as the computers are. So in drafting the programme of study for our Education Ministry, the Department for Education asked the British Computer Society, Royal Academy of Engineering, to act as honest brokers and to draw together around a big conference table a range of different stakeholders. So you have representative bodies of industry, of education there. You have people from big tech firms such as Google, such as Microsoft Research, such as Toshiba. You have people from universities such as University of Roehampton, myself, as well as actual teachers, all gathering around the table and trying to come to some degree of consensus about what we should teach. We took as a starting point the way of thinking about computing that the Royal Society, our leading learned society, had established in their report, Shut Down or Restart, that said computing should be seen as having three elements: computer science, information technology, and digital literacy. I saw those in terms of the foundations of the discipline, its applications in terms of getting useful things done, as well as considering the implications of that for us as individuals and for us as a society. The question, how does Google work, can be answered in all three domains here. In the middle layer, the IT layer, you type words in and click the button. And yes, there is more to it than that. At the computer science layer, this is about making a cached copy of the accessible web, of indexing that, of using the PageRank algorithm to rank results in terms of the number and quality of inbound links. So there's lots of computer science going on behind the screen when we type in our search query. But there's also an implications layer to that. How does Google work? Well, by building up a very detailed profile of us as individual users and knowing which adverts we're most likely to click on if they're displayed alongside our search results. And being able to use Google, yes, of course that matters. But also, there should be some understanding of the principles that underpin Google, as well as a consideration of the implications of our perhaps over-reliance on it. The opening sentence of our new curriculum starts with this level of ambition. A high-quality computing education equips pupils to use computational thinking, which you heard of earlier, and creativity to understand and change the world. And we think this is what education should do. It should equip young people to understand the world in which they find themselves, and yes, be empowered to make a difference to that world. Creativity is tremendously important, and we were doing lots of creative use of technology under the old curriculum. The new thing here, computational thinking, is worth talking about a little, because this is the golden thread that runs throughout our computing curriculum. And we think of computational thinking as a way of looking at problems, of looking at systems in such a way that a computer can help us solve them, or a computer can help us understand them. For the Barefoot Computing Project, which is a primary professional development program, we identified 6 concepts that underpin this way of looking at problems, this way of looking at systems. That computers are deterministic machines, set them up the same way, and they will produce the same output. That we look at algorithms, the sequence of steps, the sets of rules. That we break big problems down into smaller parts. That we look for patterns, we try to generalize a way of solving problems. I love the phrase that a good computer scientist is a lazy computer scientist. That for Jeanette Wing, abstraction lied at the heart of this, of trying to manage the complexity of systems and putting this at multiple levels there. And yes, stepping back and evaluating whether the solution is a good one. We also, particularly for primary, emphasize a number of approaches to exploring problems, things like play and tinkering, things like making things, of fixing things when they go wrong. And it's lovely hearing already about how young people are taking that idea of debugging something and applying it beyond code to their work in first language, to their work in mathematics, of persevering when it gets hard, and it does get hard. And yes, working collaboratively, although not generally for exam work. So let's have a look at what we have on the curriculum. And this is going to be a whirlwind tour. We start with our very, very youngest children in a thing which we call early years foundation stage, although I do think kindergarten has a much better ring to it. So the children before the age of 5, we don't teach them to program computers. We do teach them to solve problems and to look at systems in a way which hints at that computational thinking. So we want children by the age of 5 to, yes, have their own ideas, to be able to make links between one idea and another, and to choose their own way of doing things. And these sorts of processes lie at the foundation of what becomes computational thinking when we throw technology in later on. So what sort of thing happens in our kindergarten? Well, children will tackle their own sorts of problems, and the problems they choose to tackle will often be big problems that an individual on their own couldn't tackle. Children will be asked to sort things out, to classify things according to their properties. The computer scientists in the room are thinking about objects and classes here, I hope. Children will work collaboratively to solve really big problems. I worry a little about the gender differences already on that bottom left picture. Do you notice how the boys are doing the manual work, as the girls are taking an advisory or managerial role to the process? And we have kindergarten teachers who put on their desk things like the thinker saw and the trier saw and the explorer saw. You can't get away with that further up school. But those attitudes are one which we hope children will continue to have throughout their time in school. So then on to the first stage of formal education, the work we do with 5 to 7-year-olds, and we introduce the technical term algorithm at this point. And we had a lot of advisor and consultants who were very worried about using technical language like that. We talk about algorithms, though, as sequences of steps of sets of rules, and we give real-world practical examples, such as how do you share a bunch of sweets amongst 3 or 4 or 5 people? What are the rules, what are the steps you go through in order to make that happen? We do have children implementing their algorithm as a program on a digital device. Yes, that can be a computer in the traditional sense, but it's more likely with children at this age to be the floor turtle, to be the robot. We have there the blue bot. Again, my daughter not just programming the blue box, but teaching her doll how to program the blue box. Don't worry, I really do. But we don't want children just writing programs. We want children thinking about programs. So being able to use logical reasoning, which is something that really ought to be taught in school, to be able to predict what a program will do, rather than just clicking on the green flag and running the code. To be able to step back and do the code comprehension thing of what will this program do when I run it. Very, very important. On then to the second part of elementary education, 7 to 11-year-olds. They're writing by this point relatively complex programs that draw on ideas of sequence, selection, repetition, input, output, variables. So being able to not just play a drill and practice maths game by the age of 11, but create your own drill and practice maths game by the age of 11 is what we're looking at in terms of primary education. And we use the block-based languages. We're not typing code in. We're snapping building blocks of programs together because that reduces the cognitive load that's involved with writing a computer program tremendously. We also want children, again, reasoning logically, being able to spot what the mistake is in a program, rather than just running the program and trying to find the error that way, but being able to reason logically about the program that they've written or that they've been given and see how they can improve on that. There's more to this than just programming, so we want children, by the end of primary school, to understand how the internet works and how the internet makes the World Wide Web possible, and that the internet and the web are not the same thing. Into secondary education now, for 11 to 14-year-olds, we include the idea of the computational abstraction, of taking a real-world situation and modelling that on a computer, of determining what the state and behaviour of that system is, of the rules that govern how the system evolves. The example here is the spread of an epidemic across the population. So we are preparing our 11 to 14-year-olds for the zombie apocalypse. Okay, and we then have the theoretical foundation of computer science, so an understanding of key algorithms, such as algorithms for search and such as algorithms for sort. And yes, being able to implement that as code matters, but an understanding of the algorithm can be something you do by just sorting weights into order. We want children to understand how hardware, how software work and how they're related together. And that's hard to do if you're working on a Windows PC or a smartphone. It really is. So if you're working on one of these incredibly simple, tiny wee devices, this BBC microbit, it's much easier to get down to that layer of how the software and the hardware are interrelated. And as you heard earlier, our national broadcaster, the BBC, putting one of these into the hands of every 11-year-old in the country, not to their schools, but to the children themselves. It's going to be tremendously exciting seeing what our young people do with this sort of technology. So we get to that point by the age of 14. What happens beyond there? Well, at this point we step back a little and we say there should be a minimum entitlement, but we're not going to insist that every young person studies computer science beyond the age of 14. So we have a unique language in our national curriculum that pupils should have the opportunity to study. Everywhere else it lists what pupils should be taught, but for computing between 14 and 16, it says there's the opportunity to study further elements of computer science, further elements of ICT or IT. And the opportunity to study could be for a qualification, and we have qualifications in this space, but it could be doing a massive open online course of MOOC, such as Harvard's CS50, which is truly excellent introduction to the principles of computer science. The minimum entitlement is relatively simple, and broadly speaking, just is continue with the work between 11 and 14. So this can be taught across the curriculum for every young person, but some will then choose to study this for a qualification. And the qualifications include, yes, more theory, more understanding how programs work, but also some of the sort of practical hands-on programming challenges, such as creating one of those drill and practice programs for a tied primary school. At 16 to 18, there is no longer any entitlement to this, but there's the opportunity to continue to study a qualification. And the qualifications that have been developed in this space are really very ambitious ones, introducing ideas like functional programming, which previously used to be left to university computer science courses and bringing those to our school leavers. And again, the project, the practical programming task, and here to get the highest grades, the student themselves must select a difficult problem to work on and guidance as to what a difficult problem is. We're seeing this course, these qualifications, the 16 to 18 qualifications in computer science, yes, as preparation for university degrees in computer science, and we hope more of our young people will go on to study this subject, but also as a really good preparation for lots of other subjects. What university course in engineering, or in physics, or in mathematics, or in economics doesn't require some ability to program a computer? Because the cutting edge of these domains is one which is determined, at least in part, by computation. And so for young people wanting to study other subjects at university, we think an 18-plus qualification in computer science is a very useful one to have. I'm conscious of time passing. Let me talk to you a little about what we've done as an organisation, Computing at School, to facilitate the implementation of this vision. We have in Britain something of an era of small government, of government stepping back from things which they don't see that they have to do themselves. The phrase that is used on the government's website is government should only do what only government can do. So our government has specified a curriculum that should be taught, but have stepped back from implementing that curriculum, of providing training or providing resources or providing ways in which this can be done, and left that to other groups to fill that space. The challenge, CS for All in the States put this very well, the hardest part of getting great computer science in every school is getting a great computer science teacher in every school. It will surprise you, I'm sure, that many of our graduate computer scientists choose not to become secondary school teachers, and even fewer become primary school teachers. In this subject, we're expecting teachers to teach something that many of them were never taught themselves. This isn't an insurmountable challenge, but it is a challenge. So we've aimed for the low-hanging fruit. We've said, what makes outstanding computing teaching? It's great pedagogy. There's a great set of technology skills. You have to be able to use the computers. But it's also this knowledge of computer science. And we've said, as a group computing at schools, we're not going to worry yet about the pedagogy, the how to teach it. We're not going to worry about the technology skills. We're going to do all we can to fill in the gaps in terms of computer science subject knowledge. Our government has made suggestions for what effective professional development looks like, and they're of the view that the best sort of professional development is teachers working with other teachers to plan lessons, to develop resources, to find ways to solve problems. Surprisingly, at the end of a very long but very interesting morning, not sitting and listening to somebody show you PowerPoint slides. So Computing at Schools as an organisation has made those connections between teachers. We started 7 years ago now with a very small group of people who could sit round a conference table in Cambridge and have grown almost exponentially for a period there. So we now have close on 25,000 members. These are primary school teachers, these are secondary school teachers. These are also academic computer scientists, people working in the software industry who are helping with this process because they care about the outcome of this process. We've moved to a regional model recently where we have 10 partner universities who look after the teachers and the hubs and the master teachers, the experts in their area, and facilitate training and make the connections between teachers and other teachers. We have close over 200 local hubs of teachers meeting together after school, once a term, possibly more frequently than that, having some coffee, having some cake, and then sharing their stories, their resources, their insights into what makes effective computing teaching. Our education ministry has funded 400 master teachers to be the lead practitioners in their area, each taking responsibility for close on 40 schools in their neighbourhood and having some time each week, as well as their actual classroom teaching, to go and help teachers in other schools near them and understand the ideas of computer science and, gain some experience in what makes effective teaching of this subject. We've produced a number of resources there, all of which are under a liberal Creative Commons license. The slide has links to the material if you'd like to pursue that further. People often ask me, what impact are you seeing? And my excuse at the moment is it's too early to tell. This only went on to our national curriculum 2 years ago, so this is still very early days. And we don't have the rigorous research into what is actually happening in school, although we're working on that now. What we do have is some early indications from the number of students who are choosing to pursue qualifications. So our 16 plus qualification, GCSE, you see the red line at the bottom there, a rapid increase over the last couple of years in the number of students who are choosing to take a 16 plus qualification in computer science. I think many of us see that trend as set to continue. At 18 plus, the picture does give some cause for optimism, but it's probably too early to tell. The red line is those taking an 18 plus qualification in computing, and we're starting eventually to see an uptrend in that. But we hope that that will continue and indeed pick up further. At university level, the number of students applying for undergraduate computer science courses has picked up over the last couple of years. And as more students get excited about this subject at school, we hope that this trend also will continue. The last thing I want to say before we go to lunch is the really radical thing we've done in terms of computer science education is, as Tim Berners-Lee put it in the tweet at the London Olympics 2012, this is for everyone. By putting it onto the national curriculum and making it an entitlement for every child in the country, it is no longer something which is just for those who have parents who are interested in the subject or those who want to become software engineers or programmers when they grow up, or just the geeky few, or just the boys, heaven forbid, or just those in nice middle-class schools. This is an entitlement for every child. And that's really the radical vision of what we're trying to do with computer science education. I'm not going to do questions now because we have the panel later, but if you want to get in touch, you'll have another look at the slides. The details are on the slide behind me. Thank you very much.